A divisibility rule is a shorthand way of determining whether a given number is divisible by a fixed divisor without performing the division, usually by examining its digits. Although there are divisibility tests for numbers in any radix, and they are all different, this article presents rules and examples only for decimal numbers. Divisibility rules for numbers 1 €20. The rules given below transform a given number into a generally smaller number, while preserving divisibility by the divisor of interest. Therefore, unless otherwise noted, the resulting number should be evaluated for divisibility by the same divisor. In some cases the process can be iterated until the divisibility is obvious. For others the result must be examined by other means. For divisors with multiple rules, the rules are generally ordered first for those appropriate for numbers with many digits, then those useful for numbers with fewer digits. Note: to test divisibility by any number that can be expressed as 2n or 5n, in which n is a positive integer, just examine the last n digits. Step-by-step examples: divisibility by 2. First, take any number and note the last digit in the number, discarding the other digits. Then take that digit while ignoring the rest of the number and determine if it is divisible by 2. If it is divisible by 2, then the original number is divisible by 2. Example: 376, 37 6, 6 a 2 equals 3, 376 a 2 equals 188, divisibility by 3 or 9. First, take any number and add together each digit in the number. Then take that sum and determine if it is divisible by 3. The original number is divisible by 3 if and only if the final number is divisible by 3. If a number is a multiplication of 3 consecutive numbers, then that number is always divisible by 3. This is useful for when the number takes the form of a x, 492, 4 plus 9 plus 2 equals 15, 15 is divisible by 3, at which point we can stop. Alternatively, we can continue using the same method if the number is still too large. 1 plus 5 equals 6, 6 of 3 equals 2, 492 of 3 equals 164, x, 336, 6 a, 7 a, 8 equals 336, 336 of 3 equals 112. Divisibility by 4. The basic rule for divisibility by 4 is that if the number formed by the last two digits in a number is divisible by 4, the original number is divisible by 4. This is because 100 is divisible by 4, and so adding hundreds, thousands, etc. is simply adding another number that is divisible by 4. If any number ends in a two-digit number that you know is divisible by 4, then the whole number will be divisible by 4 regardless of what is before the last two digits. Alternatively, one can simply divide the number by 2, and then check the result to find if it is divisible by 2. If it is, the original number is divisible by 4. In addition, the result of this test is the same as the original number divided by 4. X general rule: 2092, 2092, 92 of 4 equals 23, 2092 of 4 equals 523. Alternative example: 1720, 1720 of 2 equals 860, 860 of 2 equals 430, 1720 of 4 equals 430. Divisibility by 5. Divisibility by 5 is easily determined by checking the last digit in the number, and seeing if it is either 0 or 5. If the last number is either 0 or 5, the entire number is divisible by 5. If the last digit in the number is 0, then the result will be the remaining digits multiplied by 2. For example, the number 40 ends in a 0, so take the remaining digits and multiply that by 2. The result is the same as the result of 40 divided by 5, 40/5 equals 8. If the last digit in the number is 5, then the result will be the remaining digits multiplied by 2, plus 1. For example, the number 125 ends in a 5, so take the remaining digits, multiply them by 2, then add 1. The result is the same as the result of 125 divided by 5. X if the last digit is 0. 110, 11 0, 11 0, 11 a, 2 equals 22, 110 of 5 equals 22, if the last digit is 5, 85, 85, 85, 8 a, 2 equals 16, 16 plus 1 equals 17, 85 of 5 equals 17. Divisibility by 6. Divisibility by 6 is determined by checking the original number to see if it is both an even number and divisible by 3. This is the best test to use. If the number is divisible by 6, take the original number and divide it by 2. Then, take that result and divide it by 3. This result is the same as the original number divided by 6. X. General rule, 324, 324 a 3 equals 108, 324 a 2 equals 162 or 108 a 2 equals 54, 324 a 6 equals 54, finding a remainder of a number when divided by 6, 1, a 2, a 2, a 2, a 2, and a 2 goes on for the rest, no period. Minimum magnitude sequence, 1, 4, 4, 4, 4, and 4 goes on for the rest. Positive sequence, multiply the rightmost digit by the leftmost digit in the sequence and multiply the second rightmost digit by the second leftmost digit in the sequence and so on. Next, compute the sum of all the values and take the remainder on division by 6. Example, what is the remainder when 1,036,125,837 is divided by 6? Multiplication of the rightmost digit equals 1 a, 7 equals 7, multiplication of the second rightmost digit equals 3a, a2 equals a 6, third rightmost digit equals a 16, fourth rightmost digit equals a 10, fifth rightmost digit equals a 4, sixth rightmost digit equals a 2, seventh rightmost digit equals a 12, eighth rightmost digit equals a 6, ninth rightmost digit equals 0. 10th rightmost digit equals a 2, sum equals a 51 a Parmel 3, remainder equals 3, divisibility by 7. Divisibility by 7 can be tested by a recursive method. A number of the form 10 za plus ay is divisible by 7 if and only if za aa2y is divisible by 7. In other words, subtract twice the last digit from the number formed by the remaining digits. Continue to do this until a number known to be divisible by 7 is obtained. The original number is divisible by 7 if and only if the number obtained using this procedure is divisible by 7. For example, the number 371, 37aaa, 2a, 1, equals a37aaa 2 and equals a35. 3aaa, 2aa, a5, equals a3aaa 10 equals aa7. Thus, since a7 is divisible by 7, 371 is divisible by R7. Another method is multiplication by 3. A number of the form 10 za plus ay has the same remainder when divided by 7 as 3 za plus a y. One must multiply the leftmost digit of the original number by 3, add the next digit, take the remainder when divided by 7, and continue from the beginning, multiply by 3, add the next digit, etc. For example, the number 371, 3a, 3 plus 7 equals 16 remainder 2, and 2a, 3 plus 1 equals 7. This method can be used to find the remainder of division by 7. A more complicated algorithm for testing divisibility by 7 uses the fact that 100 aa per mel equal or less than 1, 101 aa per mel equal or less than 3, 102 aa per mel equal or less than 2, 103 aa per mel equal or less than 6, 104 aa per mel equal or less than 4, 105 aa per mel equal or less than 5, 106 aa per mel equal or less than 1. Mode 7. Take each digit of the number in reverse order, multiplying them successively by the digits 1, 3, 2, 6, 4, 5, repeating with this sequence of multipliers as long as necessary, and adding the products. The original number is divisible by 7 if and only if the number obtained using this procedure is divisible by 7. This method can be simplified by removing the need to multiply. All it would take with this simplification is to memorize the sequence above, and to add and subtract, but always working with one-digit numbers. The simplification goes as follows. Take for instance the number 371, change all occurrences of 7, 8 or 9 into 0, 1 and 2, respectively. In this example, we get 301. This second step may be skipped, except for the leftmost digit, but following it may facilitate calculations later on. Now convert the first digit into the following digit in the sequence 13,264,513. In our example, 3 becomes 2. Add the result in the previous step to the second digit of the number, and substitute the result for both digits, leaving all remaining digits unmodified. 2a plus a0 equals a2. So 301 becomes 21. Repeat the procedure until you have a recognizable multiple of 7, or to make sure, a number between 0 and 6. So, starting from 21, take the first digit and convert it into the following in the sequence above. 2 becomes 6. Then add this to the second digit, 6a plus a1 equals a7. If at any point the first digit is 8 or 9, these become 1 or 2, respectively. But if it is a 7 it should become 0, only if no other digits follow. Otherwise, it should simply be dropped. This is because that 7 would have become 0, and numbers with at least 2 digits before the decimal dot do not begin with 0, which is useless. According to this, our 7 becomes a 0. If through this procedure you obtain a 0 or any recognizable multiple of 7, then the original number is a multiple of 7. If you obtain any number from 1 to 6, that will indicate how much you should subtract from the original number to get a multiple of a 7. In other words, you will find the remainder of dividing the number by 7. For example, take the number a 186, first, change the 8 into a 1, 116. Now, change 1 into the following digit in the sequence, add it to the second digit, and write the result instead of both, 3a plus a1 equals a4. So 116 becomes now 46. Repeat the procedure, since the number is greater than 7. Now, 4 becomes 5, which must be added to 6. That is 11. Repeat the procedure one more time, 1 becomes 3, which is added to the second digit, 3a plus a1 equals a4. Now we have a number lower than 7, and this number is the remainder of dividing 186/7. So 186 minus a 4, which is 182, must be a multiple of a 7. Note, the reason why this works is that if we have a plus b equals c and b is a multiple of any given number n, then a and c will necessarily produce the same remainder when divided by n. In other words, in 2a plus a7 equals a9, 7 is divisible by r7. So 2 and 9 must have the same remainder when divided by 7. The remainder is a 2. Therefore, if a number n is a multiple of 7, then adding multiples of 7 cannot possibly change that property. What this procedure does, as explained above for most divisibility rules, is simply subtract little by little multiples of 7 from the original number until reaching a number that is small enough for us to remember whether it is a multiple of 7. If 1 becomes a 3 in the following decimal position, that is just the same as converting 10a, 10n into a 3a, 10n. And that is actually the same as subtracting 7a, 10n from 10a, 10n. Similarly, when you turn a 3 into a 2 in the following decimal position, you are turning 30a, 10n into 2a, 10n, which is the same as subtracting 30a, 10 now 28a, 10n, and this is again subtracting a multiple of 7. The same reason applies for all the remaining conversions, 20a, 10 now a 6a, 10n equals 14a, 10n, 60a, 10 now a 4a, 10n equals 56a, 10n, 40a, 10 now a 5a, 10n equals 35a, 10n, 50a, 10 now a 1a, 10n equals 49a, 10n. First method example, 1050 a 105 a 0 equals 105 a 10 a 10 equals 0. Answer, 1050 is divisible by 7. Second method example, 1050 a 0501 a 0a, 1 plus 5a, 3 plus 0a, 2 plus 1a, 6 equals 0 plus 15 plus 0 plus 6 equals 21. Answer, 1050 is divisible by 7. Vedic method of divisibility by Auscultation. Divisibility by 7 can be tested by multiplication by the Ekladikar. Convert the divisor 7 to the 9's family by multiplying by 7. 7a, 7 equals 49. Add 1, drop the units digit and, take the 5, the ekha as the multiplier. Start on the right. Multiply by 5, add the product to the next digit to the left. Set down that result on a line below that digit. Repeat that method of multiplying the units digit by 5 and adding that product to the number of tens. Add the result to the next digit to the left. Write down that result below the digit. Continue to the end. If the end result is 0 or a multiple of 7, then yes, the number is divisible by 7. Otherwise, it is not. This follows the Vedic ideal, one-line notation. Vedic method example. Is 438,722,025 divisible by 7? Multiplier equals 5. 438,722,025, 42 37 46 37 6 40 37 27, yes. Pohlmann-Euromass method of divisibility by 7. The Pohlmann-Euromass method provides a quick solution that can determine if most integers are divisible by 7 in 3 steps or less. This method could be useful in a mathematics competition such as math counts, where time is a factor to determine the solution without a calculator in the sprint round. Step A, if the integer is 1000 or less, subtract twice the last digit from the number formed by the remaining digits. If the result is a multiple of 7, then so is the original number. For example, 112 11 equals 11 4 equals 7 yes, 98 9 equals 9 16 equals 7 yes, 634 63 equals 63 8 equals 55 no. Because 1001 is divisible by 7, an interesting pattern develops for repeating sets of 1, 2, or 3 digits that form 6-digit numbers and that all such numbers are divisible by 7. For example, 001001 equals 1001/7 equals 143, 010010 equals 10,010/7 equals 1430, 011011 equals 11,011/7 equals 1573, 100 equals 100,100/7 equals 14,300. 101 equals 101,101/7 equals 14,443, 110 equals 110,110/7 equals 15,730. 010101 equals 10,101/7 equals 1,443, 10 equals 101,010/7 equals 14,430. 111,111/7 equals 15,873, 222,222/7 equals 31,746, 999,999/7 equals 142,857. 576,576/7 equals 82,368. For all of the above examples, subtracting the first 3 digits from the last 3 results in a multiple of 7. Notice that leading zeros are permitted to form a 6-digit pattern. This phenomenon forms the basis for steps B and C. Step B, if the integer is between 1001 and 1,000,000, find a repeating pattern of 1, 2, or 3 digits that forms a 6-digit number that is close to the integer. If the positive difference is less than 1000, apply step A. This can be done by subtracting the first 3 digits from the last 3 digits. For example, 341,355 or 341,341 equals 14 equals 18 equals 7 yes, 67,326 067. 067 equals 259.25 equals 25 and 18 equals 7 yes. The fact that 999,999 is a multiple of 7 can be used for determining divisibility of integers larger than 1,000,000 by reducing the integer to a 6-digit number that can be determined using step B. This can be done easily by adding the digits left of the first 6 to the last 6 and follow with step A. Step C, If the integer is larger than 1 million, subtract the nearest multiple of 999,999 and then apply step B. For even larger numbers, use larger sets such as 12 digits and so on. Then, break the integer into a smaller number that can be solved using step B. For example, 22,862,420 equals 22,862,420 or 21,999,978 862,420 plus 22 equals 862,442, 862,442 862 or 442 equals 420 42 and equals 42 yes. This allows adding and subtracting alternating sets of 3 digits to determine divisibility by 7. Understanding these patterns allows you to quickly calculate divisibility of 7 as seen in the following examples. Pomana Euromass method of divisibility by 7. Examples. Is 98 divisible by 7? 98 9 equals 9 is 16 equals a 7 yes. Is 634 divisible by 7? 634 63 equals 63 08 equals 55 no. Is 355,341 divisible by 7? 355,341 or 341,341 equals 14,001 14 equals 1 equals 108 equals a 7 yes. Is 42,341,530 divisible by 7? 42,341,530 341,530 plus 42 equals 341,572, 341,572 or 341,341 equals 231, 231 23 equals 23 or 2 equals 21 yes. Using quick alternating additions and subtractions, 42,341,530 530 or 341 equals 189 plus 42 equals 231 23 equals 21 yes. Multiplication by 3 method of divisibility by 7, examples. Is 98 divisible by 7? 98 9 remainder 2 2a, 3 plus 8 equals 14 yes. Is 634 divisible by 7? 634 6a, 3 plus 3 equals 21 remainder 00a, 3 plus 4 equals 4 no. Is 355,341 divisible by 7? 3 times 3 plus 5 equals 14 remainder 00a, 3 plus 5 equals 5a, 3 plus 3 equals 18 remainder 4a, 3 plus 4 equals 16 remainder 2a. 3 plus 1 equals 7 yes. Find remainder of 1,036,125,837 divided by 7, 1a, 3 plus 0 equals 3, 3a, 3 plus 3 equals 12 remainder 5, 5a, 3 plus 6 equals 21 remainder 0, 0a, 3 plus 1 equals 1, 1a, 3 plus 2 equals 5, 5a, 3 plus 5 equals 20 remainder 6, 6a, 3 plus 8 equals 26 remainder 5, 5a, 3 plus 3 equals 18 remainder 4, 4a, 3 plus 7 equals 19 remainder 5, answer is 5. Finding remainder of a number when divided by 7, 7 a period, 6 digits. Recurring numbers, 1, 3, 2, a 1, a 3, a 2, minimum magnitude sequence, 1, 3, 2, 6, 4, 5, cycle repeats for the next 6 digits, period, 6 digits. Recurring numbers, 1, 3, 2, 6, 4, 5, positive sequence, multiply the rightmost digit by the leftmost digit in the sequence and multiply the second rightmost digit by the second leftmost digit in the sequence and so on and so forth. Next, compute the sum of all the values and take the modulus of 7. Example, what is the remainder when 1,036,125,837 is divided by 7? Multiplication of the rightmost digit equals 1 7 equals 7, Multiplication of the second rightmost digit equals 3, 3 equals 9, third rightmost digit equals 8, 2 equals 16, fourth rightmost digit equals 5a, a1 equals a 5, fifth rightmost digit equals 2a, a3 equals a 6, sixth rightmost digit equals 1a, a2 equals a 2, seventh rightmost digit equals 6, 1 equals 6, eighth rightmost digit equals 3, 3 equals 9, ninth rightmost digit equals 0, tenth rightmost digit equals 1a, a1 equals a 1, sum equals 33, 33 modulus 7 equals 5, remainder equals 5, digit pair method of divisibility by 7. This method uses 1, a 3, 2 pattern on the digit pairs. That is, the divisibility of any number by 7 can be tested by first separating the number into digit pairs, and then applying the algorithm on 3-digit pairs. When the number is smaller than 6 digits, then for 0 a €1 register trademark S to the right side until there are 6 digits. When the number is larger than 6 digits, then repeat the cycle on the next 6-digit group and then add the results. Repeat the algorithm until the result is a small number. The original number is divisible by 7 if and only if the number obtained using this algorithm is divisible by 7. This method is especially suitable for large numbers. Example 1, the number to be tested is 157,514. First we separate the number into 3-digit pairs, 15, 75 and 14. Then we apply the algorithm, 1 15 3 75 plus 2 14 equals 182, because the resulting 182 is less than 6 digits, we add 0 a €1 registered trademark S to the right side until it is 6 digits. Then we apply our algorithm again, 1 18 3 20 plus 2 0 equals a 42, the result of 42 is divisible by 7, thus the original number 157,514 is divisible by 7. Example 2, the number to be tested is 15,751,537,186. 1 15 3 75 plus 2 15, plus equals a 180 plus 103 equals a 77, the result of 77 is divisible by 7, thus the original number 15,751,537,186 is divisible by 7. Divisibility by 13, remainder test 13. If you are not comfortable with negative numbers, then use the sequence. Multiply the rightmost digit of the number with the leftmost number in the sequence shown above and the second rightmost digit to the second leftmost digit of the number in the sequence. The cycle goes on. Example, what is the remainder when 321 is divided by 13? Using the first sequence, ANDs, 1 plus 2a, a3 plus 3a, a4 equals 9, remainder equals a 17 mod 13 equals 9. Example, what is the remainder when 1,234,567 is divided by 13? Using the second sequence, answer, 7 1 plus 6 10 plus 5 9 plus 4 12 plus 3 3 plus 2 4 plus 1 1 equals 178 mod 13 equals 9, remainder equals 9, beyond 20. Divisibility properties can be determined in two ways, depending on the type of the divisor. Composite divisors, a number is divisible by a given divisor if it is divisible by the highest power of each of its prime factors. For example, to determine divisibility by 24, check divisibility by 8 and by 3. Note that checking 4 and 6, or 2 and 12, would not be sufficient. A table of prime factors may be useful. A composite divisor may also have a rule formed using the same procedure as for a prime divisor, given below, with the caveat that the manipulations involved may not introduce any factor which is present in the divisor. For instance, one cannot make a rule for 14 that involves multiplying the equation by 7. This is not an issue for prime divisors because they have no smaller factors. Prime divisors, the goal is to find an inverse to 10 modulo the prime and use that as a multiplier to make the divisibility of the original number by that prime depend on the divisibility of the new number by the same prime. Using 17 as an example, since 10 equals a 50 equals 1 mod 17, we get the rule for using AA5x in the table above. In fact, this rule for prime divisors besides 2 and 5 is really a rule for divisibility by any integer relatively prime to 10. This is why the last divisibility condition in the tables above and below for any number relatively prime to 10 has the same kind of form. Notable examples: the following table provides rules for a few more notable divisors. Generalized divisibility rule, to test for divisibility by d, where d ends in 1, 3, 7, or 9, the following method can be used. Find any multiple of d ending in 9. Then add 1 and divide by 10, denoting the result as m. Then a number n equals 10t plus q is divisible by d if and only if mq plus t is divisible by d. For example, to determine if 913 equals 10a, 91 plus 3 is divisible by 11, find that m equals a 10 equals 10. Then mq plus t equals 10a, 3 plus 91 equals 121. This is divisible by 11, so 913 is also divisible by 11. As another example, to determine if 689 equals 10a, 68 plus 9 is divisible by 53, find that m equals a 10 equals 16. Then mq plus t equals 16a, 9 plus 68 equals 212, which is divisible by 53. So 689 is also divisible by 53. Proofs: proof using basic algebra. Many of the simpler rules can be produced using only algebraic manipulation, creating binomials and rearranging them. By writing a number as the sum of each digit times a power of 10, each digit's power can be manipulated individually. Case where all digits are summed, this method works for divisors that are factors of 10. AAA1 equals 9. Using 3 as an example, 3 divides 9 and equals a 10 AAA1. That means the same for all the higher powers of 10, they are all congruent to 1 modulo 3. Since two things that are congruent modulo 3 are either both divisible by 3 or both not, we can interchange values that are congruent modulo 3. So, in a number such as the following, we can replace all the powers of 10 by 1, which is exactly the sum of the digits. Case where the alternating sum of digits is used, this method works for divisors that are factors of 10 plus 1 equals 11. Using 11 as an example, 11 divides 11 equals a 10 plus a1. That means, for the higher powers of 10, they are congruent to 1 for even powers and congruent to a 1 for odd powers. Like the previous case, we can substitute powers of 10 with congruent values, which is also the difference between the sum of digits at odd positions and the sum of digits at even positions. Case where only the last digit, s, matter. This applies to divisors that are a factor of a power of 10. This is because sufficiently high powers of the base are multiples of the divisor, and can be eliminated. For example, in base 10, the factors of 101 include 2, 5, and 10. Therefore, divisibility by 2, 5, and 10 only depend on whether the last one digit is divisible by those divisors. The factors of 102 include 4 and 25, and divisibility by those only depend on the last two digits. Case where only the last digit, s, are removed, most numbers do not divide 9 or 10 evenly, but do divide a higher power of 10n or 10 In this case the number is still written in powers of 10, but not fully expanded. For example, 7 does not divide 9 or 10, but does divide 98, which is close to 100. Thus, proceed from, where in this case a is any integer, and b can range from 0 to 99. Next. And again expanding. And after eliminating the known multiple of 7, the result is, which is the rule double the number formed by all but the last two digits, then add the last two digits. Case where the last digit, s, is multiplied by a factor, the representation of the number may also be multiplied by any number relatively prime to the divisor without changing its divisibility. After observing that 7 divides 21, we can perform the following. After multiplying by 2, this becomes an n. Eliminating the 21 gives, and multiplying by a 1 gives Either of the last two rules may be used, depending on which is easier to perform. They correspond to the rule subtract twice the last digit from the rest. Proof using modular arithmetic. This section will illustrate the basic method. All the rules can be derived following the same procedure. The following requires a basic rounding in modular arithmetic. For divisibility other than by 2s and 5s, the proofs rest on the basic fact that 10 mod m is invertible if 10 and m are relatively prime. For 2n or 5n, only the last n digits need to be checked. Representing x as, and the divisibility of x is the same as that of z. For 7, since 10a, 5a per ml equal or less than 10a, a per ml equal or less than 1a, mod 7, we can do the following, representing x as. So x is divisible by 7 if and only if y2z is divisible by 7. Notes, A B C D E F G H I J K L M N O P. This follows from Pascal's criterion. See Kissanen, pages 100-101. A B C D E F G H I J K L M N O. A number is divisible by 2m, 5m or 10m if and only if the number formed by the last m digits is divisible by that number. See Richmond and Richmond, pages 105, AB Apostle, pages 108, ABCD Richmond and Richmond, section 3.4, pages 102-108, ABCDEFGHIJKL Richmond and Richmond, section 3.4, theorem 3.4.3, pages 107, AB Kissanen, pages 101, http www.tavers.net/ index.php op equal article ampersand sid equal 3358. New divisibility by 13 rule was found by Etham Dynek, Turkish teacher, Su, Francis. Divisibility by 7 Mud Math Fun Facts. Retrieved December 12, 2006. Page 274, Vedic Mathematics, 16 Simple Mathematical Formulae, by Swami Sankaracharya, published by Motilal Banarsidass, Varanasi, India, 1965, Delhi, 1978. 367 pages. Dunkels, Andrus, comments on Note 82.53. A generalized test for divisibility, Mathematical Gazette 84, March 2000, 79-81. References, Apostle, Tom M. Introduction to Analytic Number Theory. Undergraduate Texts in Mathematics 1. Springer Verlag. ISBN A978-0-387-90163-3. Kissanen, Branislav. Mathematical Problems and Proofs, Combinatorics, Number Theory, and Geometry. Plenum Press. ISBN A978-0-306-45967-2. Richmond, Bettina. Richmond, Thomas. A Discrete Transition to Advanced Mathematics. Pure and Applied Undergraduate Texts 3. American Mathematical Soc. ISBN A978-0-8218-4789-3. External links. Interactive divisibility lesson on these rules, divisibility criteria at Cut the Knot, divisibility by 9 and 11 at Cut the Knot, divisibility by 7 at Cut the Knot, divisibility by 81 at Cut the Knot, divisibility by 3 explained, stupid divisibility tricks, divisibility rules for 2 to 100.